All right. I think that's working. Very good. Welcome everybody to the lab meeting. I just give the date, so it's August 23rd. So great to have such a nice lab. Let's do a quick round of introductions. I think everybody knows me, so let's start with Peter.
I'm Peter. I'm a 4+1 here. This is, I guess, my second year in the 4+1, but yeah, I'm conducting research into deer overpopulation within the nature preserve, trying to use UAV, thermal and LiDAR sensing to do that.
Awesome.
Hi, Alana. I'm also a 4+1, so we're all kind of in this together. It's nice to meet you. And yeah, I'm looking at proxying economic development and activity using daytime satellite imagery. Yeah, I'm excited to start that process.
Cool.
Happy to be.
Hi, I'm Liam. I'm just a regular master's student. I graduated from Virginia Tech in the spring. I am more interested in doing remote sensing and LiDAR in terms of application in archaeology.
Awesome.
Hi, I'm Shruta, just a regular master's student, second year master's student. I'm from the Earth Sciences department. And my research is more of near surface geophysics, where I'm trying to attempt to move from a hyperspectral to a multispectral framework using a low cost UAV and sensor system to detect landmines.
Good.
Yeah, my name is Bakman. I'm from Ghana, and I'm also a grad student, first year geography. Yes, I'm interested in UAVs and LiDAR. I have background in GIS.
And urban work, right?
Yeah.
Urban planning. Very good.
Yeah.
All right, so this is a good mix of people, a lot of overlap, which is fantastic. I'm really excited to see how these projects shape up. I think everyone's had a little bit of an introduction to the lab. We'll kind of get more of it as we go, but I think now everybody is connected to GitHub. Everybody is connected to Slack. So that's the two big things. And we'll work to kind of fill in whatever gaps we have. I realized this morning that I'm going to need to make sure everybody has access to the Google Drive. So I'll probably send something out about that. We try to meet every week. We'll do individual meetings as well, either weekly or bi-weekly or whatever is needed for whatever we're doing. But the lab meetings are a good chance to sort of share ideas with people, to learn from each other. I really enjoy these. The lab meeting culture was, my advisor tried briefly to kind of get that going, but it didn't really stick. But we've been doing this here in the Neal Lab for 6 or 7 years now. And so we've got a pretty big archive of topics. I think many people have seen this, but maybe not everybody. So this is the lab wiki. This is one of the places, this is kind of the purpose for the GitHub site. I have my own GitHub. I guess this is linked to that. But you know, my regular GitHub is for, you know, projects and coding and whatever, but I realized many years ago that we were going to need a wiki, right? Because the content that we generate weekly and the things that we do, that's a good way to share knowledge, but it doesn't stick anywhere without some central repository. And so wiki seemed a good framework to store all of that knowledge as we go. So we've got, so basically that's all there is here. There's probably a couple of images that are actually linked in the wiki. There's no real software here, it's all wiki. There's the kind of landing page. Sam Tarani designed this logo a few years ago. A little introduction to the lab and some looks at equipment and things like that. I shared this link on the Slack channel, but this is a 2023 slideshow, kind of a lot of the projects that have been done in previous years. I'll update that over the next couple of months, and it will include the things that you all are working on. So I'm excited about that. The Zoom link is here. The link to the website is there. And there's a lot of individual articles of varying completeness. So some of these are really stubs, right? Like stuff I kind of started on and made notes on, but not super complete. So 3D tiles is something that I added not too long ago. It's pretty short little stub. It talks about what 3D tiles are, which is a way to store point clouds and meshes that you might generate in LiDAR or structural motion UAV scanning, and share those with the world, right? So it's a data format, but it's also sort of this mechanism to share stuff out. The coolest example of this is probably Google has a complete 3D tile set for the world that's like super amazing. And it interfaces with virtual reality, and this is kind of and web stuff, but the virtual reality stuff is super cool. Virtual reality, one of the tools that we use is A-Frame. This is kind of just a collection of links, right? There's not much going on here. BusyBee is kind of a medium grade wiki page, right? This is a drone that I designed and built. It's 3D printed, it's got aluminum arms, it's all built out of components. I just like that stuff, but also it's really useful because you can get like blue UAV components. You can maybe potentially fly this on like federal projects, right? Instead of having to use a DJI thing or something that you buy. And it's really inexpensive to build and it's really easy to repair. It was sort of designed to be a good field drone so that if I'm out and about and I crash it and I fix it. I actually did crash this drone in Mexico and had to fix it in Mexico with 3 different parts that I bought, and it totally succeeded. And that's all documented in a lab report that I did back in the day. There's big things in here. So like UAV, drone. I try to have sort of like titles that are searchable here. This is the big page, right? So we've got like lots of stuff in here about this. So this is kind of a mid-grade page, I guess I would say. Structure from motion is a really good page, I think. So lots of stuff going on here, just encapsulating, data sets that you might want to sort of practice, all kinds of stuff in here. So I hope that this is going to be useful for training, right? As I need to get people up to speed on LiDAR, I can like send you to the LiDAR page, and you can get started on sort of what I think are sort of the key bits here to get going. A lot of that's links to stuff, right? I'm not trying to author a bunch of content. Like I'm trying to like get you trained on what to speed. So like, I know Noah has a really good LiDAR lecture that I always recommend to people. Like that's linked on here. Anyway, so the wiki I hope will come in handy. The other thing that's here though, is the lab report archive, which is itself just a wiki page of all of these meetings that we do. And it goes back years. So you can see the first meetings that we recorded back in 2018, probably not the first meeting that we did, but it's the first meeting we were like, hey, we should record these so that we have them. And in fact, we just started by like, well, we'll just save the PowerPoints, right? And then at some point, it wasn't far beyond that. We're like, let's just record them because then the whole thing is there. So we do a recording, we've got the PowerPoints and we got the PDFs for everything everybody's done for the last 6 years. I maintain all of this. I've always kind of wanted to hand that off to a grad student, but I guess I'm kind of picky about what shows up. Now I've got it. But one thing that I do require is that when you submit lab reports, that they're in the specific name format, and that's so that I don't have to like rename 8 files per week. That makes me pull my hair out. So, but otherwise, it's all good. So we'll go ahead and get started today. Peter and I are the only ones presenting today. Next time, what I'd like to do is have each of you 4 present. You should present every week. If something happened and you're sick or you got run over by a truck that week, like, okay, that's fine. Or if you're out of town or whatever. This is a regular thing, and it will help drive you forward as you go. What else should I say about lab meetings?
I think that's pretty much it, really. Like,
They vary in length. I tend to go long. I don't know why. Mine are like half an hour, 40 minutes. I don't expect that from everybody who's here all day. But I tend to have like a lot of little tidbits to share, and whatever it is I'm working on. So for next time, especially your first year, I think good things to do are like article presentations. Like I read this piece and like, here's what it was all about. Share that with the group, right? Because we're going to be interested. The research that you're doing, I conducted this, analysis on Google Earth Engine or whatever, and here's the results, and here's what I got, and here's what I'm planning to do next week. So they tend to take a form where the first page has a bunch of keywords, I would advise you to try to have keywords that are pretty specific. So don't just put LiDAR. And the reason for that is we're a kind of a LiDAR lab. So like, that doesn't help us discriminate what you did that week from what everybody else did all the other weeks. So like, you know, try to be specific. So like mine, Rapa Nui Atlas, New View Space LiDAR coming soon, Esri graphic for drones, aircraft satellites, FTM 3D viewers. So these are like keywords that are sort of like quite specific about whatever it is. So I have, you know, titles from that slide are often really pretty quick to throw in there. They can be pretty specific. The goal is, the reason that these are here is that when somebody's like, oh, I presented on 3D tiles a while back, what did I do? I gotta go back and find it. Like, what are the words that are gonna help you or someone else find that material? All right. And then we present them the stuff. They're pretty they're pretty off the cuff. So I don't expect you to spend lots of time preparing these. These are like screenshots and bullet points and like, you know, it's like ephemeral content, right? Stuff I'm getting out there. I do suggest that, especially as you're getting into the second year of your master's and you're preparing figures, try to prepare really nice figures sometimes that you think might go in your thesis, because then you're done, right? Like, I did that thesis or I did that image and now it just goes in my thesis and it drops right in. So you can help yourself by sometimes doing things that are like production quality. And then at the end of the slide, deck, you usually have goals, like what am I working on next? And that's a really good process to sort of say, what's the next step for me? I also really like to include, as we go, last week's goals and how they turned out, right? So you're accountable to yourself about like, well, I said I was going to do this stuff. Did I do it? Like sometimes yes and sometimes no. But like, you want to get to the point where mostly you're doing what you said you're going to do. There's always going to be a couple things that you add in. There's always going to be a couple things you didn't get to. But by and large, set your goal and meet your goal. That's the plan, right? So we'll get started. When we upload these, we've got Google Drive space. They're kind of small. I guess I don't want to change the font size in progress here, but I'll do it next time. So I know this is really small, we'll change it. The format for naming looks like this. So last name and then the date in a very particular format. So name all in lowercase, period, the date, year, month, day, and that's so that it sorts correctly. And then that's for other stuff. And then .pdf. And you'll upload both the PDF and the PowerPoint. You can author your content in like Google Slides or whatever, but when you export it out, I need it as a PDF, as PowerPoint for saving. And then I'll get you guys access to Google Drive so you can upload these things. So you'll upload these things before the lab meeting. I would really encourage you to try to get these done the night before. Lab reports that are done in the 5 minutes before you get to here are not good lab reports. Get them done the night before, upload them. Think of something in the morning you want to change, go ahead and do it. But like, don't make these a last minute thing. Ideally, you're building them as you go per week, during the week, right? So I don't write my lab report on Thursday night. I write my lab report Friday afternoon through Thursday night, right? I do a thing, I take some screenshots, I write about it. Take some screenshots, I write about it. So I build it up as I go. Mostly that works. And sometimes you got to edit some stuff down, but build it as you go during the week. Don't save it up to the end. All right, let's get to it. By convention, I always go first. And then everybody just kind of rotate through. We usually do kind of the home team, and then if there's people on the Zoom, then they go second. Right. I do want to make sure, I also should make sure that this is recorded. I don't think I have any other microphones. Okay. Okay, so I tend to be pretty wordy on my keywords, as you can see. The first part of my lab reports, it's like a lot of cool stuff that I ran into that I'm sort of like bookmarking and communicating. So that you don't all have to do this. If you do find something that you think is cool, you want to share, great, throw it on in there. And I'll also note, memes are totally welcome. Don't take these things super seriously. Have fun with it, right? So it's okay to like let your hair down a little bit at these lab meetings. All right, so this was a cool thing that I saw that I really liked. There is a way to add the ability to talk to a Linux formatted USB stick or SD card in Windows subsystem for Linux. That's pretty dense, so I'm gonna talk through that. Windows subsystem for Linux, which there's a wiki article for, is a way to run Linux native apps on your Windows computer. So in the old days, and still, you can install Linux on a separate computer. You can install it as a separate partition on your computer. You can dual boot. But one of the things that Windows added in Windows 10 was the ability to run Windows or run Linux basically natively as Windows is running. So if there are Linux tools that you want to use to do a job, they're right there at your fingertips, and it's super easy to get started with that. You go to the Microsoft Store, you type in WSL, and you can just install it, and bam, you've got Linux available right away. And Linux is great, because there's a ton of cool tools in Linux that are just not available on the Windows side, or different, or harder to use, or whatever. So FFmpeg is a tool that I use to take apart video and images. What else do I use on the Linux side? If I want to use wget to like download 10,000 files from a NASA server, I'll use it on the Linux side because that version is really way better than the other stuff. Windows 10 can do it. Windows 11 lets you do it graphically, so you can actually do graphical Linux programs on that side. The reason that this is really exciting for me is because even though it's Linux running in Windows, it's not totally all there, right? So like most of it's there, you can do almost everything. But one of the LiDARs that I have, which is laying in this cabinet, will write to either an NTFS or an ext4 formatted partition. So that's like a Windows partition, Windows style data storage or Linux style data storage. But if you write it to the Windows style, it drops frames. So if I'm making a LiDAR scan, every 10th frame or something is just gone. And I think it's worse than that. I think it's like 30% of the frames are gone. So I have to write it to a Linux partition. Okay, great, I can do that. Now, how do I get it? You can't just plug a USB stick that's Linux formatted into a Windows machine and start reading it. You can, there's software out there that will let you do it, but it's this sort of like third-party stuff that doesn't look super legit to me. It probably is legit, but like I'm sort of gotten away from these like third-party tools that like you don't know what they're from, right? And these are university machines, and you can't just go installing random stuff on them. So if I can access that data through a Linux partition on Windows, like I'm really excited, right? This lets me write out my LiDAR data the way that I want and get it without the need to these extra tools using the system I'm already comfortable with. I haven't tried it out yet, but I'm glad to know it's there. It's a good one for Tarifa. Carl found this the other day when we were doing our drone flights in the Solomons. Colin was using ropes to suspend his magnetometer. So we fly the drone, and there's these four ropes coming down from the drone arms, connecting to this big styrofoam thing that holds a magnetometer. And a magnetometer is a cool way to detect, well, what's a magnetometer? It detects
magnetic anomalies.
So metal, and also magnetometers can be used to detect like burnt material, is that right?
I think so.
So like prehistoric fires or something, right? Like you could determine like there was a fire here and it changes the chemical composition in a way that a magnetometer can read. Has to be far away from the drone because electrical interference is going to screw up the signal. And so you've got to get it far. And so when you're flying it on a drone, Colin was using ropes, and that was the way it was done. But as we were flying it, you can imagine those ropes are kind of unstable, and so they kind of move around. You can do some things to try to fix that. But this is kind of a neat way to mount it in a way so that magnetometer isn't swinging all the time, which makes the data cleaner, which makes it easier to do the data analysis. You think you guys would get something like this, or?
So I know that Alex, my advisor, they collected magnetic data or magnetometry. They used that to collect some data over the summer, but I think they use kind of the same technique.
With the ropes?
Yeah.
Yeah. The problem with the ropes is it's really hard to keep it from swinging. Like,
It was swinging a lot. The instrument was pretty big as well, so I don't know if they've looked at the data yet, but I know that there is a shared Google Drive and they're supposed to upload the data.
okay. Well, let them know about this. So there's this, and then there it is in flight, which is not super impressive. But, oh, the cool thing that I was gonna say is that, the company that makes this has a YouTube page, so you can actually see it in flight. I wanted to see it take off and land, because that was actually the trickier part. Flying it, it was unstable and it did swing, and that's a problem for the data. For me as the pilot, it was a problem because it starts to sort of impact the flight characteristics of the craft. It's a long lever arm. And so we thought, well, if it's rigid or semi-rigid, then that wouldn't do that as much. And if it had like a hinge on it, and the way that you take off, my drone, and here's my payload. The way that you take off is you connect these with ropes, and then I would lift off, and then the ropes would kind of go tight, and I'd fly over, and then I'd go up. And then when I landed, I would kind of land, get it settled on the ground, and then walk the drone forward like that. Not terrifically tricky piloting. I was mostly worried that the ropes were gonna like get in the propellers or something, but it wasn't so bad. So I imagine that it probably lifts off the same way. It's just a lever arm that connects it to the ropes. I'll note also that one, not everything in a lab report is for everyone, right? Like if you're like, I don't really care about magnetometers, that's fine. Like I hope that you're enjoying all of the other riffraff that comes your way, but not everyone will engage with everything, and that's fine. And then, yeah, here's something else. Qixing Wu is a faculty member at Tennessee. He actually used to be at Binghamton, which is awesome. I haven't met him yet, but I'm really looking forward to it at some point. I'm sure I will. Qixing Wu is the probably the best person I know that works with Google Earth Engine. He develops a lot of really cool tools. He's got a textbook on it that he wrote. And he often uses like Python and Jupyter notebooks to do that stuff. A lot of GE is JavaScript, but he's kind of a Python person. He is also really into Planetary Computer, which I am as well. It's Microsoft's version of Google Earth Engine. And he posted this on LinkedIn, which is that maybe possibly Microsoft is sort of shutting down some of their Planetary Computer stuff. I don't know how far this goes. One of the lead developers got laid off, and so were a lot of people on his team. But they then clarified that like not everybody got laid off, it's still around. Planetary Computer is really great because it's got LiDAR. So the Google Earth Engine doesn't, it has LiDAR products, but it doesn't have the LiDAR point clouds. And I could get those with Planetary Computer and process my LiDAR data in the cloud, which is cool. Without ever having to download it and process it, which can be a real pain. So that was kind of interesting. We are starting to plan our next missions. Solomon's round 2 may happen in about a year. So we'd be going to back to do another LiDAR survey. We're going to try to make the case that you can't fly regular drones on federal land. DJI is outright prohibited. But these days they also have what's called a blue list, which means that things have been sort of vetted. And not only are they not Chinese made, but the components aren't Chinese made either. Very worried about that stuff on federal land. So Astro is one drone made by the company FreeFly that's on this blue list. And they have 2 wonderful LiDAR payloads that I did not know about. So the HoverMap SPX, which is a SLAM-based LiDAR, which in this case means that the head of the LiDAR spins. So a LiDAR will always go around, not always, but this particular LiDAR goes around like this. And then the whole head spins as well. So it's kind of imaging everything all the time. So that's kind of neat. Pitched a little bit as sort of like potentially useful for like under the canopy stuff, which is great. And then the Recipe Ouster OS1 64. I also didn't know that these payloads were standardized, which is cool. DJI has their own sort of standardized payload attachment. You just like put it up there, there's a socket, you twist it, and you're good to go. But I didn't know that there was an open source version of that. Open source is kind of an alternative version of that. Our LiDAR, for instance, is totally isolated. It's not, it doesn't connect to anything. It's got a power cable, you plug it in, and then otherwise it's entirely self-contained. But this means that like the hover mount, for instance, could be used for collision detection, right? You're flying it through somewhere, and that LiDAR can then be used to image in real time how the drone, what its environment is like, so it doesn't run into a building or something. Matt, Bandy, who I'm working with on this like remote sensing symposium that I'm gonna be at next week, had mentioned, that he uses the Auterion mission control software. I hadn't heard of that. Has anybody flown with Auterion? We'll have to try checking it out. He seemed to like it. There are a lot of flight control softwares out there now. I mean, we've got a page of those on the UAV wiki. Gunjan documented those a while back. There's like 20 of them that are common. Esri just released those, their own, not too long ago, but there's no Android version, so I'm not gonna get to test it, but yeah, lots of flight control software out there of varying quality. I'm throwing this up here mostly kind of as a note to myself. This is a pretty neat LiDAR archaeology project in the Amazon. I think you did look at this
Yeah.
already. So this is the second time that it's getting referenced, but it's a really pretty image of an ancient, 2,500-year-old site that's imaged in the Amazon. There's a ton of LiDAR out there, just sort of like revealing things that we don't know. I haven't seen, so the big places where this is getting done, Central America was huge. So a ton of Mayan stuff was imaged with LiDAR, and they're still, they've been doing that for like 15 years. They're kind of keeping that program rolling. This is stuff in the Amazon, stuff that's like way out there that just hasn't been imaged. So this is all really cool stuff. And it rewrites our understanding of like what these like pre-Columbian societies were like, because we just totally don't know. And this is like, I mean, not only is this pre-Columbian, but like way pre-Columbian. So really interesting. Southeast Asia is another hotspot, so there's a ton of LiDAR being done there. I haven't heard about a lot of the stuff being done in Africa. Do you know about archaeological LiDAR?
No.
Yeah.
I've never heard of anything like
Keep
that.
your ears open. I'm interested. I would think that it would be just as valuable, right? Because there's gonna be a ton of stuff that could get imaged in much the same way. So I don't know. We pay for like one mission, to like find something. Usually the way this stuff gets done is of one site and then you image around it. And then you're like, oh, look at all this other stuff that fed into, it's like a city, right? It's not just like here, it's like the supporting settlements that are all around it. So that would be the way to start, I would think. We're in the middle of a computer build. So this is this machine right now. It's not the one I'm running this presentation on, but it's in progress. This came about because Carl was trying to run some of his Rapa Nui stuff from Easter Island. He's got like 50,000, 70,000 images that he needs to stitch together. And a standard sort of lab machine might have 10 cores on it. This machine that I'm presenting on last year had 10 cores. I upgraded that to 18 over the summer, which is very good. And then we needed something better than that. So we built a 64 core machine. And actually, I just put in another RAM stick this morning. So now it's got 256 gigs of RAM. We're going to go all the way up to 512, I think, which is half a terabyte. It's got a 4090 graphics card. They made a mistake on the imaging. So they swapped my drives. So they're going to have to take it back and re-image it again. Thank you to everyone who's been helping me keep the doors unlocked so they can come get it. They'll have to come get it, stay and re-image it. They're going to be sad, but I was sad when I saw what had happened. So that's a bummer. These are the components. It's going to be amazing. I did some benchmarking on it to see how well it's going to chug through the data. Basically, we built this thing to be on spec with the ArcGIS Reality team's big computer that they were running their stuff on. My computer is my computer at home. It's a perfectly adequate, good, above average machine. It's got 10 cores on it. It's got 120 gigs of RAM. It's got a nice graphics card in it. When you run this benchmark data set from Pix4D, Pix4D Mapper takes a little over 25 minutes. Matic, which is an updated version of that software, takes about half that time. The computer that we have right here executes that same data set 21 minutes with Mapper, and I haven't run it with Matic yet. But the new machine that we just built, takes that time down to 7 minutes with Matic. So it's a big improvement. And then this is a small data set, and I think that those gains are going to be even bigger as the data set gets bigger. So like the reason that we built this thing was it was taking Carl like 2 weeks to run a data set. And then it's never right the first time. So you got to rerun it, and sometimes you got to rerun it, and like that happens a lot. So you got to run that data set 5 or 6 times, which is not so unusual. It's like 2 months of your life while you're waiting to do. So this is supposed to take that down to a couple of days instead of a couple of weeks. I've had a bunch of deer in my yard. This is Peter. I sent him this on Slack, so he's seen it before. I wanted to take a real photo with an RGB camera, but this is the back window out of my house. This is the tree line. This is the lawn with the just grass and stuff. This is the water feature. So this is actually water. But these are apple trees, and the deer have been coming by several times per day to eat the apples off of my apple trees. We were wondering, what does a deer look like on these thermal cameras? Because we've been imaging this stuff from overhead. We've been doing this for a couple of years. We've got some good stuff from that, but sometimes when we fly, we don't get any deer. And one time we got one thing that we don't really know what it is.
Yeah.
So the question is, like, how many pixels is a deer with a thermal camera? And you can run the calculations like, okay, is a deer is this big, and you should be able to see this. But one of the things is like, in the literature is like, you should image for deer when it's cold, right? Because then the heat of the deer is going to stand out to the cold of the environment. How much of a difference does that make? I mean, one reason is the leaves are off, right? So it's going to make it easy to do that. But just like apart from the leaf off situation, what does it look like? So this is what it looks like. That is a deer with this resolution of camera. So shows up, it doesn't look like a deer. If I didn't tell you it was a deer, you wouldn't know. Distance there, I need to measure, walk it off, but it's probably on the order of like 60 feet, 70 feet, something like that. So it's 20 or 30 yards, 30-ish yards maybe. 30 meters-ish. Yeah, I don't know. It's not great, but that's where the camera, this is where resolution matters, right? So one of the problems with thermal cameras is they're really low resolution. This one is 256 by 192, which is just a little like USB camera that you can plug in with your phone. But even the really good stuff, the stuff that we were using to image was only like 640 by 512, which is terrible. The very new stuff looks like it's 128 by whatever. But resolution really matters. RGB cameras are really good, right? 20 megapixel camera is nothing, but these are like, I forget, 0.2 megapixels or something. It's very, very small. I got a note in my, you'll develop, or you have developed, like, alerts on Google Scholar or whatever, like new papers come out, like, ooh, let's read it. So this showed up in my inbox. Cities at the forefront of emerging US heat governance. I'm really interested in heat mapping. So this article came out and it caught my eye. Sarah Miro is the lead author. She's done a ton of cool stuff on urban resilience broadly. This is the first time that I've run into any of her stuff. One of the things that I'll emphasize for the new graduate students especially, science is driven by people. It's like people that are doing the research and like that you want to talk to. Like sometimes it's easy as a student to be like distant from the creation of that knowledge, right? It's like you go to class and you learn about it. But like actually it's just like Sarah's working on this stuff, and when you think of it that way, it's a real person that you can talk to and has a body of work and you can, so humanizing research is important to me. And so I wanted to make contact with Sarah. And the reason is that Binghamton doesn't have access to this article, and neither did Virginia Tech. Actually, I tried that one. And so I couldn't get a hold of it. Faculty members are often, you should always do your work to try to like find articles, but you totally can email people and be like, hi, Sarah, I'm so-and-so. Could you send me your article? And they'll be like, sure, here you go. People like it when you email them, like respectfully and, like I said, do the work and like try to find it, but like, can't find it, like, they're happy to help you out. So, so I made contact with Sarah, which was great. Talked to her a little bit about some of the work we do here. Her lab is the Planning for Urban Resilience Lab. She's got a center, which I meant to make a note of here, but didn't. That seems like they do really interesting parallel work to at least like the thermal part of the stuff that I'm doing. So probably try to continue to make contact with them. All right, the last couple of things here. One of the big projects that I'm working on still at Virginia Tech is the Build project. This is where we've got sensors inside of a building, and we're using them to track movement through the system, right? So a person walks through, we've got point clouds that are generated once per second as they go through that, and we fuse all of the each individual point cloud for each of the 14 gets fused into one big point cloud and several derivative projects. When we started the project, we had 11 sensors. We added 3 more, but we ran them as parallel separate projects all last year. And then this year we wanted to merge those together. So we had one single 14 sensor project. The code that you write, I'm hoping to teach a Python programming class in the spring. For those of you who are coders, maybe if you're not, whenever you're coding, you're trying to solve the problem at that moment, but you're also trying to like solve that problem systematically entirely, right? So it was fun to go back and revisit code that I had written at the beginning of this project, basically, to see how good of a job I did writing it such that I can go from 11 sensors to 14 sensors. Because sometimes you write this stuff and you sort of like, I gotta get this done. And you take some shortcuts, and that's normal. But you also try to like plan ahead. And in this case, I think it was not so bad. The area that we were adding was this spot over here. So this is sort of a render of some of the LiDAR data. And this is the area that we were imaging with the new sensors. And so this was actually a weird GIS problem. One of the cool things about this layer is that we had to create our own coordinate reference system that plugs into bigger, wider systems so that all of our stuff is referenced locally, right? So we're the 0 point for this data set is right here. This is our latitude, longitude 0, so to speak. And so everything is like 5 meters north of that and 5 meters east of that. And this isn't even oriented northeast, southwest. This is like what makes sense for the building, right? If you look at the wall and there's like a fire evacuation plan, it's like that orientation. Like that's not north up or anything necessarily. But this was an interesting GIS project. We've got a mask that was generated because there's points on the outside of this. We wanted to sort of trim those out. And just adding, editing rasters in ArcGIS Pro, I find super annoying. So if you guys have things that you'd like about that, I'd love to hear it. But every time I do it, it's a hack job. There's a pixel editor that's supposed to make this easy. I got really excited about pixel editor last semester because I could do some things with it that were kind of difficult. I tried to use pixel editor for this and it did not work. And it's a super, like I needed to add a rectangle to that image. It was a pain. So that part was fun. I got that added in there, a little bit hacky, but it worked out just fine. And then I realized, so not only do I want to include this data, but we had planned on imaging the southern hallway right here. And we decided not to do that. We decided to put the sensors over here instead of over here. I thought about just leaving this, right? There's no harm exactly in leaving this the way it was. But as the days went on, I was like, oh, I really should trim that hallway out. Why? Because it's 200 pixels of this image, but we're taking that image twice per second for the next 4 years, right? So do I really want to throw away 200 by 1000 pixels, throwing it on a disk somewhere that's never going to go away, right? And I'm going to have to process that data. I'm going to have to load that data. So, I could improve the efficiency of this data set by, let's call it 7%, right? By throwing those pixels away. That's often a good move, right? Because that costs time and money and effort. So I decided to trim them out. That part was easy. Went back in and made the switch. Did some validation to make sure that I was getting the data that I wanted. Indeed, there's something going on in this area, at least on that particular portion, so I know that it's collecting data. It looked a little funky to me. I thought, is that good data or is that noisy data? Like, I don't know. Sometimes these sensors can be noisy. It certainly looks a little bit noisy, but I think it's real. Be keeping a close eye on it as we go. And then this is an aggregate of like, I don't know, an hour's worth of data. So things like the stairs and the pillars and things like that, and tables and chairs, those show up as kind of red because they're there all the time. And then the blue kind of smudges are the activity that recorded in that hour. Not much activity in that hour. Summertime, who knows? But it works. And I went through and I did this for a bunch of things. But you can totally see, you know, probably somebody sitting over here, like there's a bunch of stuff over there, and then somebody clearly came through this door and went over here, probably sat for a while, go away. All that signatures in the data. And then one of the big projects that I've been working on is this like Guam Solomon stuff. As part of that, we flew the CIW Woods with a number of different LiDAR sensors. So that's the area, but directionally challenged. So in this basement, I don't know which way is anything. Like it's a total maze to me. Have you guys had this experience? Yeah, weird. Anyway, keep for that.
Yeah.
But I got a window that I can look at it, like, sure, but if that window wasn't there, I'd be not sure. Anyway, so we're imaging that with some LiDAR. One of the neat things about this is ordinarily you think of the density of like, can I make a DEM or something out of the LiDAR data? And if you get 10,000 points per square meter, you're like, sure, I'll be able to make a DEM out of that. If I get 2 points per square meter, you think maybe I can make a DEM out of that. But the interesting thing is that the LiDAR doesn't penetrate through the vegetation. This is our problem in the Solomons and Guam, right? We're flying a LiDAR over very dense vegetation, but I need the ground signal. I don't need the vegetation, so I can throw all that stuff away. So we imaged this with 2 different sensors. I mean, in fact, we did it at different altitudes and a bunch of other things, but this is what we did with the DJI L2 LiDAR. And then this is what we did with the Geo MMS. And this is a side view, a little 10 by 10 meter snap, right? So just taking a little section out of that point cloud as an example. The top of the point cloud's image almost the same. This one is definitely like fuzzier. Like this one is a clearer image. Can everybody sort of see that? This is clearer and sharper. Got a lot more points here. But as you get to the bottom, clearly there's a lot more density on the ground here than there is there. And if you just throw away all of that stuff and look at just this bottom stripe and kind of flip it, now we're looking at it from the top. Like pretty good coverage here, a little thinner over there for sure, right? You can see that in the data, but this one is way worse, right? Like really good dense data over here, and then pretty thin data over there. So this is a problem for me because A, I need to know what's on the ground there, right? And I can interpolate between those points, but the bigger the spacing, the worse the interpolation, right? I'm not seeing anymore, I'm guessing. And maybe I can do that and maybe I can't. I think in the lower left of that, like an interpolation is going to be pretty bad. In the middle, probably fine. So the USGS says that you need 2 ground points for every grid cell. So if I'm making a 1 meter DEM, I need 2 ground points in that DTM to do it. The problem is that these points clump together, and those metrics, when you get down to like, okay, I don't need a 1 meter DEM, I need a 10 centimeter DEM. Well, I don't have any points at all in a lot of these 10 centimeter grid cells. So the question is, how do you measure that? How do I know what the effective ground resolution of this data set is? Because the USGS method doesn't work, right? I can't just like average them out and say, well, I got 4,000 points in that 10 by 10 meter. I can do it, because I can't, clearly not, they're splotchy. So this was a technique that I developed, sort of like running it by the people at this remote sensing symposium and see what they think. The idea is you make a DEM. I'm going to use DEM, I use as a super category for DSM, DTM, whatever, right? So it's a DEM, it's gridded elevation, it doesn't really matter what. So we grid it at 1 centimeter and we see how many cells got filled, right? And if you get 5% of the cells being filled, then that resolution is not appropriate. If you bin it at 1 meter and 100% of the cells are filled, that's great, right? You can totally, it supports that resolution of gridding. So this is a graph that shows how that proportion of cells getting filled changes as you increase the cell size. Portion is small when the grid size is small, and it approaches 100% as the grid size gets large. Why isn't it exactly 100%? Have you guys studied the modifiable areal unit problem in any of your classes? When you bin up spatial data, weird things happen. And so this is an example of weird things happening exactly where you draw the line. You draw the line here and you get this result, and you draw the line there and you get a slightly different result. So this is sort of a instability in that. But the broad trend for the L2, the good LiDAR, is that you sort of rapidly converge on this 100%. And so you can bin this data at 10 centimeter and it works, right? Like you're going to fill almost all of, you're going to fill almost all of your cells and you don't have to interpolate many. But if you try this with the LiDAR that we did actually take to the Solomons and Guam, you know, you try to bin this thing at 10 centimeter and you're only getting 40% or so of your grid cells being filled. And that's probably not enough, right? Because that's indicative of these big gaps. If those 40% were distributed evenly, then it probably would be enough. And that's kind of where, like, I like this metric. But it would be better sort of if we're measuring the size of the splotches directly. So this sort of is a better approximation than the other one, but it's still only an approximation of what I'm after. But you can see it, like, at what grid size, you know, could you do 0.5 meter with both of these? Like, definitely, like that works. But the problem is that a lot of these LiDAR companies aren't like trying to image the forest floor at 10 centimeter resolution. Like that's what we've got to do. Or 20 centimeter. So DJI definitely can do it. Ours, borderline. This is why we're going to make the pitch for the DPA to buy us a new LiDAR. That LiDAR. If it works. Although one of the things that matters too is speed. So one of the great things about the DJI is that not only am I imaging this stuff better, but I'm imaging it faster. So the DJI can fly at 15 meters per second and still get data of this quality. And I was flying the GeoMMS at 5 meters per second. So a third of the speed, which means I can cover a third of the ground. Or think of it another way, for the same job, I have to work 3 times longer to do it. It's 3 times more expensive. That's a ton, right? Like, so this is where like these on the ground flight characteristics actually make a big difference for flight planning. Like literally 3 times the expense, human expense to do that job. And not as good of quality.
Does the spinning add any benefits as far as like canopy penetration? Does it like get under there better as opposed to just straight on?
Well, the lasers all move. So they all sort of either use a mirror to like move the signal around, or in this case, like a spinning head. Totally. Like if you, so you're getting a shot here and a shot there and a shot there, and it's actually imaging forward and back in these sort of stripes. So yes, spinning does help. If you weren't spinning, in fact, we spun this one at 1200 RPM. We could have spun it at 600 or 300, but the idea was let's spin faster to try to like search for a spot in the canopy that you can penetrate, right? Like, cause you're just looking for like one tiny little hole that you can get through. I took an example image of this that I'm probably gonna, I won't show it now, but you know, if you go for a walk in the woods and you look up, like you can see the sky, right? Like it's not 100% vegetation, it's like a green roof. Like the sky pokes through that. And that's what the LiDAR is doing from the other end. It's like trying to come down and find just that hole. It just needs one little hole to get through to get to the bottom. These are just notes to myself because I run into stuff that I'm trying to calculate. What I wanted to know was, are the flight characteristics of these two things the same? I flew the GeoMMS at 25 meter spacing, but I did it in 4 directions. I did it at 0 degrees, 90 degrees, 45, and 135. Is that comparable to a L2 mission with 90% overlap, which is about 7 meter spacing? Like, is this a fair comparison? I had to run those numbers to figure that out. And so what I wanted to know was how many times could a single point expect to be imaged for each? And so my calculation is for GeoMMS, I should be seeing that point 16 times, right? Because I get it 4 times this way as I go until it's out of view. And then I get it 4 times this way until it's out of view. For the DJI, that number is 10 because it's tighter spacing. 1, 2, 3, 4, 5, 6. So according to my calculations, the GeoMMS should have been seen more, which is really interesting because one of the things that we're arguing in this, or I'm arguing in the symposium paper is, on paper, the GeoMMS should have done better. It images faster. It goes 300,000 ground return points or last returns instead of 240,000. So 60 or 1/5 better or whatever ish. So it's imaging faster. We should have had more looks at each spot, and yet it was worse. It uses the same wavelength. Why was it worse? I don't know. It's really interesting. Like the fuzziness in the point cloud, that I understand, right? That has to do with like the L2 is mounted on a gimbal. I don't know. It's really interesting, but it kind of goes to the fact that you've got to test this stuff out. Okay, so my goals, we've got a remote sensing symposium coming up. So we're off next week. I got to get Addison's paper to remote sensing. So he wrote a thesis on some of the build LiDAR, indoor LiDAR stuff. It's basically a manuscript and we just got to like get it repackaged and trim some features and get it sent out. I got to go write a GWAM report after the remote sensing symposium gets over. And then I've got 3 papers kind of waiting in the wings that I need to write, a terrain print one, build paper one, and a route asymmetry one. And then Johanna is supposed to be writing a paper one of the chapters in her dissertation, which was done a year ago, was supposed to go out for publication. So let's see if she's ready. So. All right. So for me, as always, I ran too long, but there were a lot of side explanations. Do you think you can do it in 20 minutes?
Probably. It shouldn't take too long.
I always go long, but usually not that long. Sorry, everybody. Yeah, because I don't have. I've got to find the clicker. I took it out for something. I don't know where it is.
Okay. All right, so yeah, this is my lab report. All right, so I guess I'll just start off by talking about what I did over the summer. I was
Oh, quick pause.
Yeah.
One of the things about these lab reports is like, feel free to interject, like you did at least once during my lab report, but like, these are conversations. So don't think of them as just like, sometimes we get in the habit of just sort of like lecturing, and I especially am prone to that as a professor, but like, it's conversation.
Yeah.
Yeah.
So yeah, I was lucky enough to be accepted into the NASA Develop program, which was really cool. It was really exciting. And if anybody here wants to give it a shot to try to apply, they're always like accepting. They talked about people who like applied like 3 or 4 times over before they got it. So like
You applied at least one other time, didn't you?
no,
Oh, no?
yeah,
Okay.
it was just once.
First to know.
So I got really lucky. But yeah, I was part of the Alaska Ecological Conservation 2 team. We were studying the WHA caribou calving herd, which stands for the Western Arctic herd, which is in northwestern Alaska. And we were studying their calving times in relation to vegetation dynamics. So my coworkers, they were Jackie Encinas, Levi Mitchell, and Gareth Miller. So for some of our deliverables that we created, we had a tech paper, presentation, research poster, website, social media posts, and then a bunch of data analytics. So it was a bunch of work, and especially in a 10-week period, on it, even for just 4 people, like at times that did feel like kind of overwhelming, but it was still really fun. So the map here is showing the caribou calving grounds. So site B and site A are the main core calving grounds of the caribou in northwestern Alaska, and you can see how it overlaps with the national parks and preserves in the pink, and also the National Petroleum Reserve, which has some interesting policies there. I remember talking to our partner about some of them. They don't have like it fully like understood yet, and they kind of want to like move, I guess, like rewrite some policies for the caribou in those areas. But the reason why it kind of looks like these like weird blobs is because we actually got these calving zones from a paper that our partner wrote, Kyle Jolly. he wrote a paper outlining these calving areas, and he basically kind of did like, it seemed like a kernel like density map, like a just very like basic density map of like where all the caribou were going, because he has GPS trackers on some of the caribou to like understand where they're going. So yeah. So in terms of some of the deliverables, this was our tech paper. It was basically, it felt like basically like a master's thesis. It was pretty cool to write an outline. So we were talking about NDVI analysis over in Northwestern Alaska. Our partner again was Dr. Kyle C. Jolly from the National Park Service. His main focus is in Alaska too as well. The methods that we incorporated, we used the NBAR MODIS dataset and HLS datasets. So the NBAR MODIS dataset, we got that in Google Earth Engine, which for me, that was a really cool, like first time experience to learn about Google Earth Engine. I had never used it before. That was really awesome. And then HLS was actually, which stands for Harmonized Landsat and Sentinel-2 data, which we got from our Boston University science advisors who have the like code to like get that data. Otherwise, we don't really know how else to get that data. It's like actually pretty, at least for us, it seemed pretty difficult to get otherwise. But I'm sure there's other ways to get it. But anyways, we constructed NDVI time series plots and maps that we constructed in GEE and ArcGIS Pro. And then what was interesting was that we actually calculated a different statistic called delta NDVI for each day, pretty much, for each of the images we had collected too. And yeah, I didn't fully write that out. But so delta NDVI is basically the rate of daily NDVI change. So you're kind of just subtracting like the NDVI from one day, from like day 2 to day 1. So like you're kind of getting like what was the increase from each day. So that was an interesting statistic that I had never done before. Yeah, so my coworker, Levi, kind of worked on that a lot. And this is kind of what the caribou look like. This is just our partner slide. That's Kyle's in the corner. You can't see his face. And yeah, he got some really cool pictures of caribou in Alaska. Yeah. Oh yeah, this is like kind of a little video that I created. They're kind of like stingy about like accepting videos, but let's see if I can play it. Oh, there it is. Yeah. Hopefully it's not too loud. But yeah, this is kind of like what we kind of did with GEE and how we created our images and stuff. So it's only like, it won't take like a minute. So these were the satellites we used for the NBAR MODIS project, which was the Aqua MODIS and Terra MODIS. So NBAR stands for the Nadir Bidirectional Reflectance Distribution Function Adjusted Algorithm, which basically adjusts imagery to be at like a nadir facing view, like straight down. And this is what our final product ended up looking like after we further processed it in ArcGIS Pro. And then now we go to HLS. So HLS was a Harmonized Landsat and Sentinel-2 product, which creates 30-meter resolution imagery. And it's basically a vegetation phenology metrics product. It generated max NDVI values, but other than that, it was kind of based on like date, pixels were based on dates, which was kind of interesting. And then it'll scroll to like the next image too. Like we did it over from the years 2016 to 2023. The MODIS was 2000 to 2024. So yeah.
How'd you make did you make the video?
Yeah,
How'd you do it?
just PowerPoint.
Oh, really? That's
Yeah.
really good.
Yeah, just like you export it as like a video. If you like put animations in and you export it as a video, it just does it.
All right, well, then it's good quality animation, so let's finish up.
Yeah. So this is our NBAR MODIS time series maps that we had. So these go from 2000 to 2024, and on the side you can see the plots that we created. Initially, these plots were created in Google Earth Engine, but then we extrapolated the data that we wanted, which was the maximum and median NDVI values into Excel. So then we just created plots in Excel showcasing those trends. Because the reason why we chose median is because it's because it's more resistant to outliers in the data as opposed to mean is. And maximum, we were trying to look at max greenness as well, like the greenness trends within the data. And if you look, like what's really interesting here is like a lot of them like just shoot up like with the NDVI. And what we found is the particular reason for that is snow melt. So like after the snow like melts over the ground, then there will be like pockets of vegetation that just like shoot the NDVI or straight up. So that's not actual like vegetation growth. That's like the vegetation that was there, but the snow melted. And it's the same thing for HLS. And the only difference here is that instead of showcasing median NDVI values, it's showing max NDVI values. And that's because that was like a limitation with the product. We could not get median NDVI values from it, or at least like because the data was kind of like inaccessible to us and like it was given to us basically through a third party. Like we couldn't really control like what statistics we were trying to get, and I don't even think their product had median NDVI within it. Like they have like a GitHub for their product, and it like runs through an R script and everything, but yeah, it just didn't seem to have median NDVI. But max NDVI was still pretty interesting. We were still looking at like the max green up trends too within the region, and you can see that like at least in this image, at least in these images, you can see how there's a good portion of vegetation within calving zone A, which is the core calving zone, and a lot of vegetation in calving zone B as well. So makes sense why the caribou would want to calve in these areas. But yeah, aside from that, like during the last few weeks of the summer, I was figuring out drone to map and doing some of the deer pilot reconstructions that Dr. Pingle and I had flown in the previous semester. So these reconstructions were a lot worse compared to Pix4D. The thing is that I think Pix4D has the thermal reconstructions now for like PNG images, right? Yeah, I think so. So just wanted to try that out. The 3D.
Oh, drone to map has the.
Yeah, drone to map, not Pix4D.
Yeah.
Did I say, yeah, so, I forgot to put the runtime in, but I remember it being extremely long and very, not all the images were calibrated correctly. Only got 992 out of 1,500 were calibrated.
Yeah, thermal is really hard to reconstruct because, excuse me, there's not as much variability in the landscape as with an RGB image. And then the quality of the pictures coming in is a lot lower. So instead of a 20 megapixel image, it's a lot less. Just less than one.
Yeah, and you can like see like the thermal reconstruction with this, like the other thing with like drone to map and like Esri products in general is like I just hate the interface for like 3D like reconstructions. It's like it's very difficult for me to use. I just like, at least with like Pix4D, like you click on one side of the mouse, it like changes the angle. You click on two parts of the mouse, it like lets you move around or whatever.
Yeah, the Esri stuff is nice because you got a lot of like base layers that you can bring in. Other than that, it's
Yeah,
too bad.
like. But yeah, these are the deer thermals you sent me. So I find this one, well, these are from the Facebook page, right?
Yeah.
Yeah, these are really interesting, how the deer got into like, this is probably the ground, right?
There's some, I mean, they're complaining about there's something wrong with the camera, so I don't know what, like, that's why, like, the lower left is washed out.
And it's imprinting, the bottom left is always washed out and it's imprinting. Yeah, I don't know.
I don't know about that, but the images of the deer themselves are pretty cool.
Yeah, this is pretty cool. One of the things that I kind of want to try to do is like see if I could create like a neural network that like is able to like identify the deer in these images.
Yeah, I feel like once you get to this resolution, then that starts to become really possible. Otherwise, I think it's just gonna be like a speck, right?
Yeah.
Like in these images. Nothing's gonna be able to distinguish, like, that's not a deer, but that's a deer. Like, you could maybe like size, like in some cases, but I don't know. I think it's gonna be tricky.
Is there any way to like mask out like water data? Cause I was thinking about.
Yeah,
that.
you could. Yeah. Yeah, that would help.
I was thinking that could be like a possibility for that, but like then, but how would you like mask it out, like if it was in like a video? Like, is that possible?
Well, you have to pull each frame, put a video, then you can best it out of there.
Okay. Sure. Oh yeah, and then just planning drone flights now. Definitely well, Dr. Pingel's already like basically done LiDAR over the CIW woods, so I just kind of want to look at that data again, see if I can find some deer trails.
The new folks, that's this one.
And then I kind of want to like re-image this area again, just to see if we can find anything. I know like that's not like a true deer hotspot.
So we've got, I mean, one of the things is, did I tell you that one of the batteries died on the 3T? So one of the 4 batteries is like kaput.
Okay.
But Adam Matthews has a 3E multispectral, and I think Carl just bought a multispectral. All those batteries are compatible, so we basically have like 12-ish batteries that I think we could do. So I wonder if it'd be worthwhile to just like do the whole thing, you
The
know?
whole nature preserve? Yeah, that's my that's my big goal, to get the
We
whole
could,
nature preserve.
we could do it like during the day and like get a flight plan that we know works, and then run it at night when we, you know,
It's colder and.
when it's colder and the leaves are off, but then we would know it would work. I'd be a little bit sketchy about doing it at night if we haven't flown it before,
Yeah.
but we could fly Leaf on and just like, you know, get the flight parameters tuned up now and then in November.
I think that's a good idea. I like that idea.
We just keep, like, I think we've done this twice now without catching a lot of deer.
Yeah,
It's
So-
really disconcerting because it's a lot of work to get all set up and do it and run the data and.
yeah. So I think in the meantime, I'll probably try to think of other possible like research angles. Cause it's weird, like Dylan Horvath says that the overpopulation is crazy in the nature preserve, but
Is
Yeah,
it
so-
possible to put trail cams in the nature preserve? Like, would that benefit, or do they already exist?
I'm sure we could, yeah, that's a good idea. Yeah,
we could do that.
yeah, why don't you check, that's a good idea, why don't we check and see, maybe he's got some, somebody's got some.
Yeah.
Yeah. We could set, I mean, trail cams are pretty cheap, right? Like. Anybody know? $50, $200?
Like, I imagine it can't be super expensive, like it's just like a camera.
The cheap
strapped
ones
to
on
a
Amazon.
Tree.
Yeah, look it up, we can, you know, it's like $50 or something, we just order one and
Yeah,
throw it up there.
okay, cool.
That would be useful to get a sense of like counts and things, you know, like another ground truth point where like.
Yeah.
We know, we have some idea of what's going on.
Mhm. This area, yeah, because CIW is the main hotspot, and while I walked with him through the nature preserve, he showed some deer dens, but even then, like, they kind of weren't really there. So.
Yeah.
They might have figured out the problem already.
Can you, when you're looking for trail cams, can you look and see if there are any like build your own?
Okay.
Might make for a fun project in advanced remote sensing. We're gonna do some like Arduino stuff anyway. But maybe we could build 20 of them and. Be fun. If they're cheap, but like the components of that stuff, I know the Arduinos themselves are like. $5, so like that's nothing, and then you need a battery, and then you need a tiny little you need an SD card or some way to save the data. I guess it could wind up getting to be like $30 and then you're better off just like buying, I don't know, what do we look and see?
Yeah.
Sure. Interesting, anyway, good stuff.
So yeah, just some goals. Take a look at the thermography group on Facebook. Plan drone flight throughout the nature preserve, LiDAR and thermal flights should be a good idea. And do the construction of photogrammetry of deer trails that for data that I already have. And yeah, just capture more imagery of the deer trails as well using the Pix4D capture. And yeah, and start to outline my literature review. That's something I want to start doing as well.
That's good, cool, thanks, Pete.
Yeah.
All right, we'll wrap things up. Thanks, everyone. Look forward to hearing from all of you in 2 weeks. Any questions? Anything else?
You just want us to submit the lab report. Is there anything else that you require us to upload to the GitHub?
Just, so you won't upload it, it'll be to a Google Drive link that I'll share, but it'll be, just a PowerPoint and the PDF. Yeah. All right, thanks. Have a good week. You guys have a good first week of class.
Yeah.
Yeah.
Yeah, we're good.
What are you taking, Alana?
Statistics, quantitative methods, and advanced remote sensing and 500.
Pretty standard? That's probably exactly yours.
Yeah.
Exactly yours.
And exactly yours.
yours.
You taking all 3 of those? Not the 500.
Not by
Not
much.
500
Stats?
stats and yeah, your
Yeah.
class.
All right. What are you taking?
Nothing.
Nothing. Ah, good semester.
Yeah, it's
Just
just some
games,
things.
that's it.
Very good. All right, thanks everyone. Oh, we also need to get keys for you both. If you think you'll need the lab, you can get your key to the lab.
Yeah, that'd be, oh yeah, I told the reviews like, you can't tell me you need a key. You wouldn't tell me you need a key, so.
When he asked me for the rest of them, we haven't had a chance to meet yet, so. Yep, all right, I'll send them a note about that too.
I think I told you this before, but in this one, it was just an accessory.
Yeah.
I always see them up here